Yeah, let's give ourselves a quick refresh on the product and the quotient rule, and then we will jump into some other stuff. So, again, reminder, product rule. Take the derivative of f times g, where f times g means f of x times g of x. You're going to get f prime g plus f g prime. And then, sorry, 1 second here. And then the quotient rule, we have the following. We have the derivative of f divided by g is equal to f prime times g minus f times g prime. Notice, by the way, actually, let me write the denominator, divided by g squared. Notice for the quotient rule, the numerator part looks a lot like the product rule. The only difference being that instead of addition, you have subtraction. I will also mention, for the product rule, the order doesn't matter, right? You can do f prime g plus f g prime, or you could do f g prime plus f prime g, right? Order of addition doesn't matter. Order of subtraction really matters. So for the quotient rule here, you have to make sure it's always the derivative of the top times the bottom minus the top times the derivative of the bottom. You can't get the order messed up. I mean, you can, but if you mess it up, it'll be wrong, right? Okay. So we can use these to find some derivatives. For example, I have nice examples here. Yeah, I do. Oh, also remind everybody that last time we talked about how the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. We're going to finish the list of trigonometric function derivatives today, but we're going to use these for these next couple examples. So for example, I would like to find, I don't know, the derivative of x to the fourth times cosine of x. And so to do this, we're just going to use the product rule. So the product rule says you treat each factor kind of separately. You do the derivative of the first part, 4x cubed, times the not derivative of the second part, cosine x, plus, and then we switch it. We do the not derivative of the first part, x to the fourth, times the derivative of the second part, which is going to be negative sine x. You could leave your answer like this, but it feels kind of silly to not simplify it. You should definitely simplify this as 4x cubed times cosine of x minus x to the fourth times sine of x. But there's no other, I mean, you could factor out an x cubed. We don't really do that unless you're trying to like find where this function has a horizontal tangent by setting this equal to 0. That's why you might want to factor. Similarly, we could take the derivative of something like, I had a whole list here of things. 1 sec. There we go. Yeah. Something like, I don't know, the derivative of x cubed over x squared plus 2 sine of x. And here we're going to use the quotient rule. So the derivative of this is going to be, again, here are the words I'm saying, and I really encourage you to say these things, or whatever works for you, like low d high minus high d low over low squared. That's never been my favorite. I'm always thinking it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So it's the bottom times the derivative of the top. And so I know that like the formula is f prime g minus f g prime over g squared, where f is the top and g is the bottom. But I'm usually saying it in my head as g times f prime. Right? I'm thinking of it as the bottom times the derivative of the top, just because those words roll out of my mouth easier, right? It's easier to say bottom times the derivative of the top than the derivative of the top times the bottom. Maybe not really, but to me, that's just the way it is in my brain. So bottom times derivative of the top. X squared plus 2 sine of x times the derivative of the top, 3x squared. I don't need parentheses around the 3x squared since it's only one term. I do need parentheses around this since it's got 2 pieces to it, 2 terms. Minus the top times the derivative of the bottom, which is 2x plus the derivative of 2 sine x is 2 cosine x, divided by the denominator squared. Unless someone is asking you to simplify this, don't simplify it. Leave it like this. If you were going to simplify this, the first thing I would do is factor out an x squared from each of these, since it comes out very easily. Questions about this? So without any other functions, we're kind of limited to not very interesting examples. So let's go ahead and before we get to the chain rule, which we're definitely going to get to, let's talk about the derivatives of the other 4 trig functions, which require the use of the quotient rule. So I want to find the derivative of tangent of x. Well, tangent we need to write as sine of x divided by cosine of x. And now we're going to use the quotient rule. So it's going to be the bottom times the derivative of the top. I feel like I've done something stupid here. No, I guess not. My brain is getting ahead of itself. Derivative of sine is cosine of x minus the top, which is sine of x, times the derivative of the bottom, which is negative sine of x, all divided by the denominator squared, which is cosine squared x. Okay, now we're going to simplify. So this looks kind of complicated, but it actually simplifies very, very nicely. So this is equal to, the top is cosine x times cosine x, which is cosine squared x, minus sine times minus sine is plus sine squared x, divided by cosine squared x. Can anybody tell me what is cosine squared x plus sine squared x always equal to? Anyone in the chat? Yeah, it is 1. Yes. So that's one of those trig identities that I mentioned that we definitely need to know because it does come up. It's super important that we know that, oh yeah, that there, that's equal to 1. So this is 1 over cosine squared x. 1 over cosine is the same as what? Is it secant or cosecant? It's kind of fun, not gonna lie. It's funny because my video is mirrored, so like I do this and it looks like my fingers are going backwards. Yeah, it's secant. Sorry. So 1 over cosine is secant, so 1 over cosine squared is secant squared. So the derivative tangent of x is secant squared x. We're going to do the rest of them. Yeah, I think I've got room. I'm going to leave this list up here for a second. So I'm going to write the derivative of tangent x is secant squared x. And then we're going to write the other 3 here. So the reciprocal of sine is cosecant. So we usually do sine, cosine, tangent, and then their reciprocal functions to the right of them. So we're going to do the derivative of cosecant x, and then we're going to do the derivative of secant x, and then the derivative of cotangent x. Actually, we're going to do them in the opposite order. We're going to do this one first, and then this one, then this one. So here's something worth knowing. The functions that are cofunctions of each other, meaning tangent and cotangent, secant and cosecant, as well as sine and cosine, they all have derivatives that have similar patterns. So the derivative of tangent is secant squared. The derivative of cotangent, I'm just going to tell you and then we're going to find it, is going to be, well, I'm going to put a co-function on each of those. So the derivative of tangent is secant squared. The derivative of cotangent is, oh, you can't hear me? I'm not sure why you can't hear me, Evelyn. I'm sorry to hear that. No pun intended. Okay. Maybe it's, I'm imagining it's something on your end, Evelyn. I apologize. I'm going to continue, but I hope you can get your sound settings fixed so that you can hear me. I would, if you can't think of, if you can't do anything, I would try leaving the Zoom meeting and then coming back in. That is often one of the first things to try. So give that a shot if nothing else is working. And you can't hear me, so yeah, that's super helpful. Let me type something in the chat. sorry, the thing I was saying is that if the derivative of tangent is secant squared, the derivative of cotangent is cosecant squared with a minus sign in front. We're still going to show it, but that's kind of going to be the pattern. Is you can basically take any trig derivatives, it's a regular function, you can kind of append cos in front of each of them and get the corresponding derivative for the co-function. It's kind of neat. So the derivative of cotangent of x is the derivative of cosine of x divided by sine of x, right? It's important to know that cotangent is cosine over sine. And then again, we're going to use the quotient rule. So it's the denominator times the derivative of the top, which is negative sine of x, minus the top, cosine of x, times the derivative of the denominator, which is cosine of x. Sorry. The derivative of sine is cosine, all divided by sine squared. And we get very much the same thing happening. The numerator is going to be negative sine squared x minus cosine squared x all over sine squared. I can factor out a -1 from the top, and then I'm left with sine squared x plus cosine squared x over sine squared x. The sine squared plus cosine squared, again, is equal to 1. So this is -1 times 1 over sine squared x. But 1 over sine is cosecant, so 1 over sine squared is cosecant squared. So we get negative cosecant squared x. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. I'm just taking these and saying cotangent, cosecant. And the same kind of thing is going to work for these two as well, which is kind of cool. So the names here are actually pretty important, right? It's important to think about the fact that cotangent really is the co-function of tangent. Cosecant is really the co-function of secant. Cosine is the co-function of sine. Well, let's do the last two. The last two are actually, in some ways, easier than the tangent and cotangent. You don't really need to know that trig identity for these two. Oh, yeah, sure. I'm happy to explain these. If you ever, and then I will also point out, we didn't really show the limit definition for the derivative of sine and cosine. That's usually not something that's done in this class, but if you guys want me to, either in office hours sometime, or if you really want to see it in class, I'm happy to do that. I don't think it's super duper important, but yeah, my kind of point of view with most, we should usually offer more explanation if we can. So let's talk about the derivative of secant. The derivative of secant x is equal to the derivative of 1 over cosine x. So let me make sure I didn't write something stupid here. Okay, no, I didn't. Sure. I want to make sure that right when I wrote the derivative of this, I still wrote the derivative of this. Yeah, okay, I did. So again, we're going to use the quotient rule. This is where people have to be super careful with the quotient rule, because I think that here's a mistake that happens a lot. So I'm going to do the bottom times the derivative of the top. The bottom is cosine x. And for some reason, people often want to say the derivative of the top is 1, but it's not. The derivative of 1 is what? Everybody. What's the derivative of 1? Yes. So it's going to be cosine x times 0. It's all right. So bottom times the derivative of the top minus the top times the derivative of the bottom, which is negative sine of x, all over the denominator squared. So what I really want to point out is if you have a quotient rule where the numerator is a constant, the first half of the derivative is going to be 0, because it's going to be the bottom times the derivative of your numerator, which the derivative of a constant is always going to be 0. So here's what we get, which doesn't look very nice to start off with. We've got sine of x over cosine squared of x. That is the right answer, but we never write it that way. So I'm going to rewrite this as, I'm going to break this up as 1 over cosine x times sine x over cosine x. These are still the same, right? 1 times sine is sine. Cosine times cosine is cosine squared. But then 1 over cosine is another name for secant of x. And sine x over cosine x is another name for tangent of x. So the derivative of secant of x is secant x tangent x. And I'm going to point out this is, so secant and cosecant are kind of, they're interesting derivatives in that you're taking the derivative of a function of x and you get the variable x showing up twice. That is kind of atypical for derivatives. And it definitely, it becomes kind of important when we do some chain rule problems because it can be a little bit confusing, but we'll definitely talk about that. So let me, we're going to find the derivative of cosecant, but let me prepare everyone for what it's going to be. So just like how the derivative of tangent was equal to secant squared and the derivative of cotangent was cosecant squared with a negative sign. If the derivative of secant is secant times tangent, the derivative of cosecant is going to be cosecant times cotangent with a minus sign in front. We're still going to show it, but the same pattern definitely holds. If you have a derivative of a non-cofunction equal to some stuff, you can take the derivative of its cofunction by just putting cos on the functions and adding a minus sign. I will also point out that all of the cofunctions, cosine, cosecant, and cotangent, all have negatives in their derivatives. That's a nice thing to remember. Okay, well, let's actually do cosecant so you guys can see it. So the derivative of cosecant of x is the derivative of 1 over sine of x. We're going to get the same sort of thing happening. It's going to be the bottom times the derivative of the top, which is 0, minus the top times the derivative of the denominator, which is cosine, all divided by cosine squared of x. Well, wow. No, that's dumb, right? I'm making a mistake. It's not the derivative of sine on the bottom squared, it's just sine squared. This eraser feels like it's really kind of, maybe, it feels like it got like wet or something. It looks gross. I think this eraser's done. I think this eraser is the one I'll be using from now on. Sorry about that. Yeah, so we get the same sort of deal. I've got negative cosine of x over sine squared of x. I will point out that, right, compared to this, again, these are the cofunctions. The cofunction of sine is cosine. The cofunction of cosine is sine. But this I'm going to rewrite as negative 1 over sine of x times cosine x over sine of x. 1 over sine is cosecant. Cosine over sine is cotangent. So I do get negative cosecant x cotangent x. Just like we said we would. I would really recommend everybody take the time to memorize these 6 derivatives. They will definitely not be going away ever. We need to know them. And also, I would really also recommend memorizing them in this order, meaning you want to do these ones like this. So you want to do sine, cosine, tangent. It's also nice because sine divided by cosine is equal to tangent. I do want to point out the derivative divided by the derivative is not equal to the derivative, right? The derivative of sine divided by the derivative of cosine is not equal to the derivative of tangent. But sine over cosine is tangent, and then each of these is the reciprocal functions. Reciprocal of sine is cosecant, reciprocal of cosine is secant, reciprocal of tangent is cotangent. Yeah, the reason I point out this pattern here, or this sort of way of writing it, is because it actually kind of reminds me of like verb conjugation stuff you do when you learn a foreign language. Like you have, I'm terrible at foreign languages, but like, you know, you have like the I, the you, the je, I can't remember. No, I'm terrible with French. Sorry, it's been too many years. But it's kind of like you want the pattern that you want the pattern. And it's because there are other patterns for similar functions that I think come up later. Okay, the last thing I'll say about this before we start doing some examples. One student showed me a way they like to remember this, which I think is kind of cool. Yeah, thank you, Marshall. I am, you are, they are. Thanks. Yeah, I, you, they, and then like these are like the plurals, like, or I don't know. It's been too long. Sorry. Yeah. Anyway, you, yeah. Okay. Students showed me this. So for the not sine and cosine, for all the other derivatives, they showed me this. Secant x arrow, secant x, tangent x. So they showed me that the derivative of secant is secant times tangent, and the derivative of tangent is secant times secant. It's kind of cool. It also works for if you do cosecant x, negative cosecant x, cotangent x. The derivative of cosecant is negative cosecant x times cotangent x. The derivative of cotangent x is negative cosecant x times cosecant x. This doesn't work well for everybody. Like I just remember this because I've done it a bajillion times. But this is kind of slick, I think. It takes up less space to write out, and it kind of tells you 4 derivatives in one shot. So there's also that if you like it. You don't have to use it though. All right, so in different times, I would tell my students, write this down, take a picture of it, make the holy smokes, the background or the lock screen on your phone, so that every time you look at your phone, you see the trig derivatives until you've memorized it. That might not be the best way to do it currently, but take the time somehow to memorize these because you're going to want to not have to look them up every time you're trying to figure out what's the derivative of cosine, what's the derivative of secant. We're going to try and do it enough times that I burn it into your brain. So now we can take fun derivatives like what's the derivative of the square root of x times secant of x. Now we're going to use the product rule. So it's going to be, let's see, derivative square. Well, I might actually first rewrite it as x, the derivative of x to the 1/2 times secant of x. So then it's going to be the derivative of x to the 1/2, which is 1/2 x to the negative 1/2 times secant of x plus x to the 1/2 times the derivative of secant, which is secant x times tangent x. There's your derivative using the product rule. Or we might do something like, do I have any other examples that don't use the chain rule? No, not really. We might have something like, oh yeah, let's do something terrible, like the derivative of tangent x plus 2 sine of x over x to the 5th plus 1. This is going to be gnarly. It's not so much that this is hard, it's just it's going to be big. So it's going to be the bottom times the derivative of the top. The derivative of tangent is secant squared x. The derivative of 2 sine x is 2 cosine x minus the top, tangent x plus 2 sine x times the derivative of the bottom, which is just going to be 5x to the 4th. I don't really need the parentheses around there, but they don't hurt. Divided by the denominator squared. So there's the derivative of a somewhat gnarly looking quotient. So product quotient rule, also you want to kind of make sure you practice that enough so that you can do it really, really straightforwardly, quickly without making errors. But I really think we need to talk about the chain rule. So let's go ahead and talk about the chain rule. And let me actually, before I get there, let me look at one other thing. Oh, yeah, we got loads of time. So much time. Oh, we can do that. Okay, sure. Let me do 1 or 2 more examples before we get too carried away. Sure. I believe Dr. Nguyen posted, I think it's an optional homework assignment for chapter 8.5 with all the trig stuff. I think it's 8.5. Let's look at an example that's similar to one here. So I want to find the equation of the line tangent to, let me make something up that doesn't seem too terribly awful. Sure. Let's say the function is, I don't want to be too gross here. Sure. Let's say it's, sorry, I'm just trying to come up with something that isn't extremely awful, just minorly awful. Sure, let's do something like this. Let's do 3 sine of x plus 4 cotangent of x at x equal to pi over 6. Okay. So find the equation of a tangent line. Need two things: point, slope. We have half a point. So we need the point. I mean, don't need the point first, but I mean, define the point first. So the point, we know that x is pi over 6. The y value is going to be f of pi over 6, which is going to be 3 times sine of pi over 6 plus 4 times cotangent of pi over 6. Okay, sine of pi over 6. Is it 1/2 or is it the square root of 3 over 2? It is one of those. It's 1/2, right? Pi over 6 is the smaller angle, 1/2 is the smaller value. Sine gets bigger as the angle gets bigger in the first quadrant. This is going to be 3 times 1/2 plus 4 times, let's see, cotangent of pi over 6. Cotangent is cosine over sine. I know that sine of pi over 6 is 1/2. And I know that cosine of pi over 6, I know that if sine is 1/2, the other trig function cosine is root 3 over 2. Root 3 over 2 divided by 1/2 is just root 3. So you get 4 times the square root of 3. So here's my lovely point. My point is pi over 6, comma, 3/2 plus 4 root 3. That's gross. Now let's find the derivative to find the slope. So f prime of x is going to equal derivative of 3 sine x is 3 cosine x plus the derivative cotangent to x is going to be negative cosecant squared x. So it's minus 4 cosecant squared x. All right, and then we're going to plug in pi over 6. So f prime of pi over 6 is going to be, so let's see, I already know that cosine of pi over 6 is root 3 over 2. So it's going to be 3 times root 3 over 2. And then cosecant of pi over 6. Well, let's see. Sine of pi over 6 is 1/2. So what's cosecant of pi over 6 going to be? If sine is 1/2, cosecant should be two. So I've got minus 4 times cosecant of pi over 6 is 2 squared. So here's my equally lovely slope. It's 3 root 3 over 2 minus 4 times 4 is 16. Okay, the point of this problem isn't so much that these numbers are ugly, it's that here's what you should write as your answer. So the equation here is going to be y minus the y coordinate, which is 3/2 plus 4 root 3, equal to my slope, 3 root 3 over 2 minus 16 times x minus the x coordinate. Now, usually in web work, they're asking you to solve for y. So the final answer that I would type in would be y equal to all this, 3 root 3 over 2 minus 16 times x minus pi over 6, plus this number here, plus 3 over 2 plus 4 root 3. And you shouldn't do any other simplifying, right? You should just slam this into web work and let it take care of the rest. Right? There's no reason to like get a common denominator here or anything like that. But web work has some equally gnarly equations of tangent line questions where just the slope is not nice, the point's not nice, it's all kind of just this is what you do with that. So yeah, so let us move on to the chain rule and talk about how it works and why it works. And there's kind of, I mean, there is only one chain rule, but there's kind of, we first usually talk about the power rule version of the chain rule, also known as the box method, as someone was pointing out last class, I think. So if I want to find, like, say, the derivative of, how do I want to say this? Sure, let's do it this way. if I want to find the derivative of x plus sine of x squared, I don't really need this bracket here. Yeah, I could use, well, I mean, I will use the chain rule, but for now I'm going to think of this as the derivative of x plus sine of x times x plus sine of x. So instead of using a different rule, I'm going to use the product rule, right? We're going to derive this times this. So the derivative product rule says it's the derivative of the first thing. So 1 plus cosine x times the second thing, x plus sine of x, plus then the first thing, x plus sine of x, times the derivative of the second thing, which is 1 plus cosine x. Okay, but now look. This thing and this thing are the same things, right? 1 plus cosine x times x plus sine x is the same as 1 plus cosine x times x plus sine x. So I have two of these things added together. So that's going to be 2 times 1 plus sine x times, sorry, x plus sine x, not 1 plus sine x, times 1 plus cosine x. Or to put a slightly sharper point on it, 2 times x plus sine of x to the first power times 1 plus cosine x. So this is just an example of the fact that the derivative of, say, a function squared is equal to 2 times that function to the first, like the power rule would make us do, but then we have to multiply by the derivative of the inside function. And that's that is the hallmark of the chain rule, that when you take the derivative, you kind of take the derivative of the outside part. So I've got some stuff squared, and I have the derivative of some stuff squared is 2 times my stuff to the first, but then we have to multiply by the derivative of the inside stuff. And it works kind of no matter how big your power is. It's easy to show for this example because we can easily write two things out. But it actually works if you have more things. And yeah, I feel like I should do the job of saying the bigger things. So what's the derivative of f of x cubed? Well, it's really the derivative of f times f times f. There is a triple product rule, but it's not really worth them. I mean, well, we'll say this thing here. Yeah. So there is a triple product rule. What's the derivative of f of x times g of x times h of x? I'm not going to write the of x's because it gets a little complicated, a little messy. So here's the thing. Let's think of this as this thing. Let's call it, I don't know, let's call it k. So this is the derivative of k times h. Why not take the product rule? It's going to be k prime times h plus k times h prime. Okay, no big deal, just the product rule. But then k is really f times g. So this is really equal to the derivative of f times g times h plus f times g times h prime. But now for f times g derivative, we're going to use the product rule again. So here's what you get. You get f prime g plus f g prime times h plus f times g times h prime. And distributing the h here, you get f prime times g times h plus f times g prime times h plus f times g times h prime. Okay, here's the long story made much shorter. When you take a derivative of a product of any number of things, in this case 3 things, you're going to get 3 pieces added together, and each piece will have the derivative of one thing and the not derivatives of the other things. So this one has f prime and the other two not derivatives. This one has g prime and the other two not derivatives. This one has h prime and the other two not derivatives. And this works for any number of things multiplied together. So for example, if we were going to take the derivative of 4 things multiplied together, like f times g times h times j, instead of writing it up the long way, we would just say, hey, I know it's going to be 4 things added together. The first thing is f prime times g times h times j. The next thing, instead of having f prime, we'll have g prime, and all the other things are not derivatives. And then the next one will be h prime, so f times g times h prime times j. And then the last one will be j prime, f times g times h times j prime. And I will mention, we don't really use this a lot. Like you're not usually going to be taking the derivative of something crazy, like, I don't know, something like sine of x plus x squared times, I don't know, cosine of x times tangent of x plus 1 times, this would be bonkers, secant x plus 5, right? You could, we're not going to do this because it's stupid, but you could say, okay, the derivative of this is, cosine x plus 2x times these 3 things, plus negative sine x, like the derivative of cosine, times these 3 things, plus secant squared x times these 3 things, plus secant x tangent x times these 3 things, right? No, there's definitely not. So there's no triple quotient rule. There's no quotient rule for more than 2 things. But for and that's because, right, when you divide, right, order of division matters. When you multiply, you can multiply as many things together, and the order doesn't matter. So yeah, so there's a product rule for any number of things. So back to where we were. If I want to find the derivative of f times f times f, well, it's going to be the derivative of the first thing times the other 2, plus the derivative of the second thing times the other 2, plus the derivative of the last thing times the other 2. But look, each of these things is the same. This is f squared times f prime. This is f squared times f prime. This is f squared times f prime. So what we really have here is f squared times f prime 1, 2, 3 times, or 3 times f squared times f prime. But look, that's exactly the chain rule, right? The derivative of some stuff cubed is 3 times your stuff squared, or we use the power rule for the derivative of that stuff cubed, but then we have to multiply by the derivative of the inside stuff. And so this works for any power. So it even works if your derivative is, say, the derivative of f of x to the nth power. So I think I have enough room here. Let's write it out. So if I want to find the derivative of f of x to the n, it's the derivative of f times f times f times f n times. But the however many times product rule says, all right, if I'm multiplying n things together, that means I'm going to get n pieces, right? When I was multiplying 3 things together, I got 3 things added together at the end. I'm multiplying n things together, I'm going to get n things added together. And here's what they're going to look like. The first one is going to be f prime times f times f times a bunch of f's. The next one's going to be f times f prime times f times a bunch of f's. All the way to the very last one is going to be f times f times f times a bunch of f's, except for the last one, f prime. So I know it's maybe not super easy to see everything, but so here there are n f's multiplied together. Here there are n things multiplied together. One of them is f prime, and the other n minus 1 of them are f's. And that's true for this one, and all of them, right? This has n minus 1 f's and 1 f prime. This has n minus 1 f's and 1 f prime. So, and maybe didn't have quite enough room here. So this is going to equal, yeah, f of x to the n minus 1 power times f prime of x. That's what the first one is, right? The first one is f of x to the n minus 1 times f prime. The second one is the same thing, f of x to the n minus 1 times f prime. The third one is the same thing. The fourth one is the same thing. All the way to the nth one is the same thing. So I'm adding up the same thing n times. I get n times f of x to the n minus 1 times f prime of x, which is the product, the power rule version of the chain rule. If you take the derivative of some function to the nth power, you do the power rule, you do n times your stuff to the n minus 1, and then you multiply by the derivative of the stuff. That's it. That's the power rule version of the chain rule. And then we'll talk about the larger version in a couple minutes. Well, let's do some examples. So we can do something like, I don't know, what's the derivative of sine of x plus x squared plus tangent of x to the 30th power? All right, so typically when I am looking at something that is a composition of functions, I'm usually saying it this way in my head. I've got some stuff raised to the 30th power. And the derivative of some stuff to the 30th power is going to be 30 times my stuff to the 29th power times the derivative of my stuff. It's going to be 30 times sine x plus x squared plus tangent x to the 29th power times the derivative of sine x plus x squared plus tangent x. That's always the gist, right? You leave the inside alone. You do the derivative of the outer function. The outer function here being you've got something raised to the 30th power. The 30th power is the outer function. So you differentiate that. You get 30 times leave the insides alone to the 1 less power. And then since the insides were more complicated than just x, we have to multiply by the derivative of the insides. I haven't actually found that yet, right? All I've written here is derivative of the inside. So now we should actually write it out. Usually you would probably do this in one step. You'd say it's 30 times my stuff to the 29th power times the derivative of the stuff, which is cosine x plus 2x plus secant squared x. And I want to really emphasize here, if you write it like this, you'll be a little bit wrong, because the way I've written it looks like it's 30 times sine x plus x squared plus tangent x to the 29th times cosine, and then plus 2x plus secant squared. But it should be this times the entire derivative of the stuff. So we have to have parentheses around that. So that it is this times all of this. See if I've got some more examples here. Where'd you go? Sure. Yeah. Let's do one or two more examples before we get into the more generalized version of the chain rule. Try not to murder the black pen that I always, problem is I get a new black pen. I'm like, yeah, a new black pen, it looks great. And then I use it all up and it's gone. Also, gosh, just pens. Pens. Okay, so let's find the derivative of, why don't you guys try this one? Actually, I'm going to go, yeah, I should go P, because I'm going to P. Why don't you guys try finding this derivative? The derivative of x to the 7th power plus cotangent of x raised to the 11th. Go ahead and find that derivative. Again, if you've got some stuff to the 11th power, the derivative is going to be 11 times your stuff to the 10th times the derivative of the stuff. The derivative of the stuff is going to be 7x to the 6th minus cosecant squared of x. Okay. Let's do another one, but let's do another equation of the tangent line. So find equation of the line tangent to, let's not make it too terrible, y equal to, sure, x to the 6th plus 2. Don't be stupid, James. Yeah, sure. To the 3rd power at, yeah, we can do this, sure. At x equal to 1. That should be moderately interesting. Okay, let's see what we get. So, as usual, equation of a tangent line, you need 2 things, point, slope. The point, so if you've only got x equal to 1, we need the y value. Y is going to equal 1 to the 6th plus 2 all to the 3rd. 1 plus 2 is 3. 3 to the 3rd is 27. So our point is 1 comma 27. Our slope, if you really wanted to, you could multiply this one out. I feel like this green does not look like it's showing up very well right now. Can you guys see this all right? Kind of, yeah, that's what I kind of thought. Let me do one thing here. Yeah, it's because it's also, my light's not on, which is important. Is that better? Okay. Sorry, that's why the black pen rules, because the black pen we can see. So, sorry, so we've got y equal x to the 6th plus 2 to the 3rd at x equals 1. Yeah, exactly, right? Totally agree. Black pen is supreme. So then we've got the point 1 comma 27. We're going to find the derivative. The derivative is 3 times our stuff to the 2nd power times the derivative of the stuff, which is 6x to the 5th. But what I was saying is, if you wanted to, this power is low enough that you could actually multiply it out. I don't recommend it, but you can if you really want to. But you shouldn't, so don't. So then we're going to find the derivative at 1. So we get 3 times 1 plus 2 squared times 6 times 1 to the 5th. So 3 times 3 squared is going to be 3 times 9 times 6, which is going to be kind of big. 9 times 6 is 54. 54 times 3 is, let's see, 50 times 3 is 150. 4 times 3 is 12, so 162. At least the numbers aren't super gross pi square root of garbage. So my equation here is going to be y minus 27 equal to the slope times x minus the x coordinate. That is not too terrible, right? You could definitely be not disappointed by that. And if we solve for y, you have y equal to, I'm going to actually multiply it out, 162x minus 162 plus 27. Yes, we could simplify this. It would be what? 162 minus 27 is going to be negative 135. So you can take equal to 162x minus 135. Let the person in who's trying to come in. Yeah, exactly. At least they're all whole numbers. Sorry. So many people write direct messages and I respond like everyone can see it. Someone said at least they're all whole numbers. So if I say something that's like, where is that coming from? It's because someone's written me a message and I'm responding to it. Because I'm not smart all the time about noticing if it's a direct message. So I was like, oh yeah, so-and-so said this. I'm like, oh, sorry. Usually it's not a big deal, but I try not to call people out if they've written me a direct thing. But as I'm sure all well aware, I definitely have said, oh yeah, so-and-so said such and such. Anyway, so let's go ahead and advance to talking about the generalized chain rule. So we have the power rule version of the chain rule, also known by some as the box method. If you've got the derivative of f of x to the nth power, it's n times f of x to the n minus 1 times f prime of x. And the idea I want to emphasize here is that you're taking the derivative of the outer function, right? The outer function is that we're being raised to the nth power. And the inner function is f of x. So it's the derivative of the outside function, leaving the insides alone, times f prime of x, the derivative of the inside. No worries. Yeah, no worries about it. If you actually leave and come back, that's always fine. And we'll do, so we won't prove this because it's actually somewhat complicated to prove, but I'll definitely give you an example that I think helps show it. And it involves trig, which is one of the reasons why I want trig. So the derivative of a composition of functions, f of g of x. So the idea is the same. Take the derivative of the outermost function, leave the insides alone, and then multiply by the derivative of the inside. So the derivative of f of some stuff is f prime of the leave the stuff alone, but then multiply by the derivative of the stuff. That's the chain rule. The derivative f of g of x is f prime of g of x times g prime of x. Or as I will usually say, the derivative of f of some stuff is f prime of the stuff times the derivative of the inside stuff. And this is actually, this works here if we change the names of things. So if I wanted to find, say, like the derivative of, I'm going to call the inside function g of x, right? G of x to the nth power. What we're really saying here is this is the derivative of f of g of x, where f of x is x to the nth power, right? The outer function is being raised to the nth. So f of g of x is, well, if I plug in g of x for x here, I get g of x to the nth power, which is what I'm taking the derivative of. So this would be writing out just the very general way, f prime of g of x times g prime of x. But f prime of x to the n is power rule, n times x to the n minus 1. So f prime of g of x, so if I sub in g of x for x, you get n times g of x to the n minus 1. Times g prime of x. Which is just the power rule version of the chain rule. So what I'm really trying to say with this kind of long explanation here is that this is the rule we want to know. And this is just a special sub case of that rule, where the outer function is being raised to the nth power. But you don't really need to memorize this specific version of it. You just have to remember that if you're taking a derivative of a composition of functions, we differentiate the outer function alone, but then we multiply by the derivative of the insides. Okay, let's look at an example, and then we'll actually really look at the example. So here's an example that might seem a little bit too obvious, maybe. Well, it may be too easy. Let's do it anyway. So we know that the derivative of sine of x is cosine of x. So what's the derivative of sine of 2x going to be? Well, the derivative of sine of some stuff is cosine of the stuff times what? What do I have to multiply by here? And I will say, when I ask that question, one good answer is always the derivative of the stuff, James, of course, right? Whenever we're taking the derivative of a composition, and I say, okay, you got the derivative of the outside, cosine of 2x, and then what do we multiply by? You can always be like, oh, James, it's just the derivative of the stuff. In this case, the derivative of the stuff is what? 2. Derivative of 2x is 2. So the derivative of sine of 2x is cosine of 2x times 2. And now I want to show you a deeper explanation of this. So let's actually take a look at the graphs. And I'm going to remind you that we did the graph of sine of x. Sorry, we did the derivative of sine of x graphically. Let's see. And I think, yeah, I probably have enough room here. Okay. So yeah. I'm going to draw some functions and their derivatives. I'm going to try and draw this kind of very much in line. This might be a time to use Desmos, but now I can draw the thing for you. Okay, yeah, sure. So let's see, here's 1, here's -1, here's pi, here's 2 pi. So I'm going to draw sine of x first. So sine of x, let's use some different colors here. Red, sure. So here's sine of x. It starts off at 0, 0, and then hits the point pi over 2 comma 1, and then pi 0, and then 3 pi over 2, and then 2 pi. So it looks like this. Right, so there's my sine function. Now let's draw its derivative. So its derivative, again, this is how we found the derivative to be cosine. We know the derivative is cosine. Let's make this match up here. Sorry, and I'm standing in front of the board. So again, 2 pi. I'm not going to label all the rest of these. They're the same values. So cosine hits at 0, 1, and then, right, because the slope here is 1, and the slope here is 0. The slope here is negative 1. The slope here is 0. So the tangent line here is 1. So it looks like this. And their y prime is cosine x. Okay, so now check this out. This is where it gets kind of cool. I can use this. Use a finisher. So I want to draw sine of 2x now. So how is sine of 2x different than sine of x? So sine of 2x versus sine of x. Well, sine of x is a period of 2 pi. Sine of 2x, what's the period for sine of 2x? Anybody? So here's the way I think about period. It is pi. The way I think about it is, so for sine or cosine, just regularly, the period is always 2 pi, basically. How long does it take to do one full revolution around the unit circle? 2 pi. But if I've got 2x, I need 2x to go from 0 to 2 pi. So that means if 2x needs to go between 0 and 2 pi, if I divide everything by 2, x is going to go from 0 to pi. So my period is 2 pi divided by this coefficient, which is pi. So I'm going to get the same shape, but in half the distance. So I'm going to start here, cut this into quarters again. So sine of 0 is 0, and then at the next quarter or quadrant, you get 1. And then in the next quadrant, you get 0. In the next quadrant, you get negative 1. And then the next quadrant, you get 0. So here's sine of 2x. And it repeats. So you get the same thing, right? Again, you get this. You don't really need this repeating part, but whatever. And then, cool. So there's sine of 2x in blue. Okay, let's draw its derivative, which we know is going to be something like cosine. Now here's the deal. The red one at the origin has a slope of 1. The blue one at the origin has a steeper slope of a tangent line. So that means the derivative is going to be a higher value, like 2. It is a slope of 2. I know my picture is not perfect, but it is a slope of 2. And then here at pi over 4, we're going to get a slope of 0. And then over here at pi over 2, we're going to get a negative steep slope, but it's again, it's more steep than 1. Or negative 1, it's negative 2. And then here at 3 pi over 4, we get a slope of 0. And then here at pi, we've done one full period. And at one full period, you should be back to where you started, meaning if the slope was 2 here, the slope should be 2 here. Okay, so look at what we've got. I know it's not perfect, but it essentially looks like the cosine graph, but the period is half as much. So it's cosine of 2x, right? That would be the cosine function smushed into half the period, but it's also been stretched vertically so that the amplitude is 2. Well, look at that. The derivative of sine of 2x is cosine of 2x times 2. I know this isn't a proof of the chain rule, but it does offer some visual evidence that the chain rule is in fact true. When you take the derivative of sine of some stuff, you don't just get cosine of the stuff, you get cosine of the stuff times the derivative of the inside stuff. So that's the chain rule generally, that when you take the derivative of a composition of functions, you're always going to end up multiplying by the derivative of the inside part. All right, we got 11 minutes. It's time for example palooza. All the examples. You're going to hear me say the word stuff like 1,000 times because there's always going to be some stuff. So let's say I want to find the derivative of, oh, let's not get that quite that funky yet. Let's say I want to find the derivative of, I don't know, cosine of x squared plus sine of x. So again, we're always looking at the outermost function. So the outermost function here is cosine. I've got cosine of some stuff. The derivative of cosine of some stuff is negative sine of the stuff. Some people like to underline the thing that's the stuff so they know that that's what they're going to multiply by the derivative of, or they're going to take the derivative of and multiply by. So I'm going to multiply by 2x plus cosine x. So the derivative of cosine of some stuff is negative sine of the stuff times the derivative of the stuff. That's it. How about the derivative of, oh, I know what I wanted to do. No, you're not there. Okay, fine. Let's say we have the derivative of the square root of, I'm trying not to get super complicated right off the bat. Let's do x cubed plus tangent of 2x. Sure, fine, make it a little complicated. So whenever I have a root, I usually want to rewrite it as a power before I have to take its derivative. So I would much rather imagine this as the derivative of x cubed plus tangent of 2x to the 1/2 power. And now we're going to take the derivative. I've got some stuff to the 1/2 power. So the derivative is going to be 1/2 times my stuff to the negative 1/2 times the derivative of my stuff. I kind of like to set it up so I'm just kind of filling in the blanks. So in here, this is where I want to caution everyone to be careful, right? I've seen way too many people over the years put the derivative in here. The stuff that's inside here doesn't change, right? If you've got some stuff to the 1/2, your derivative is 1/2 times this stuff left alone. Don't change it. So I got 1/2 times my unchanged stuff to the negative 1/2, right? I took the derivative of the outer function. But now we have to multiply by the derivative of the inside stuff. So the derivative of x cubed is 3x squared. And the derivative of tangent of 2x is going to require the chain rule one more time. So the derivative tangent of 2x, well, the derivative tangent of x is secant squared of x. The derivative tangent of some new stuff is secant squared of the new stuff times the derivative of that new stuff, which is 2. So there's our derivative using the chain rule. Definitely pipe up if you have questions or thoughts about what we're doing. Or need clarification. The chain rule definitely can be combined with other rules, and often is. So for example, I could ask, what is the derivative of, how do I want to do this? Sure, let's do that. Let's say I've got x squared divided by tangent cubed x plus 1. So I've got a quotient rule. Well, let's just start with that. I've got a quotient rule. So it's going to be at the bottom, tangent cubed x plus 1 times the derivative of the top, which is 2x, minus the top times the derivative of the bottom. And here's where I have to be a little bit careful. For the derivative of the bottom, the derivative of tangent cubed is not secant squared cubed. You can't take the derivative of something cubed and just say it's a derivative cubed. Derivative of tangent cubed is the derivative of tangent of x to the 3rd power. So the derivative of tangent of x to the third power is going to be 3 times my stuff to the second power. Whoa, what's going on? Everyone okay?
It turns up to the max. He ain't even playing.
Something is going on. Someone unmuted themselves accidentally. That is fine. That happens. As long as everyone's all right. Okay, I'll continue. So the derivative of tangent cubed is 3 times your stuff squared times the derivative of your stuff. This one I feel like especially people often miss. So just be careful. When you're taking the derivative of a trig function to a power, you do need to use the chain rule. All divided by tangent cubed of x plus 1 squared. I would not simplify this unless I was asked to. Let me give you guys another example. Oh yeah, let's do this one. Let's do the derivative of, yeah, we should do one like that. Let's do the derivative of secant to the fourth of x cubed plus cotangent x. Okay, this particular type of chain rule question can often be confusing identifying what is the outermost function. So are you doing secant stuff of some stuff first, or are you doing the fourth power of some stuff first? And the answer is you're doing the fourth. Well, I mean, I shouldn't really say first. That's kind of the worst way to say that. It's actually last. So in fact, let me go back for 1 second, just to kind of make sure everyone knows, right? When I'm looking at this kind of thing, cosine of x triple sine x, cosine is the outermost function. It's kind of the last thing that happens to x, right? You take x, you do x squared, then you do sine of x, then you add them together, and then at the very end, you do cosine of that. Same kind of deal here, right? The square root is the outermost function. It's the last thing that happens to your input. You do x cubed plus tangent of 2x, add them together, and then finally you take the square root of that. So I should be more careful with my language. What I call the outermost function is the last thing to happen to x. And in this case, the outermost function is being raised to the fourth power. What's the tangent? Oh, so I was writing this to make it clear that tangent cubed x is equal to tangent of x cubed, so that we can more easily see that, oh, to do the chain rule here, the derivative is going to be 3 times tangent of x squared times secant squared of x. That's what that was for. Here, whenever I have a trig function to a power, especially if there's more complicated stuff in there, I really like to rewrite it as the derivative of secant of x cubed plus cotangent x all raised to the fourth power, right? Because I'll remind everybody that when you have secant to the fourth or cosine to the third or whatever, that's just abbreviated notation for the trig function of whatever all raised to the fourth power, right? Just like tangent cubed of x really means tangent of x raised to the third power. So looking at it this way, it's more easy to visually see that the fourth power is the outermost function, right? If I was evaluating this, I would do x cubed, cotangent x, I'd add them together, then I would take secant of that, and then finally at the end, I would do the fourth power, whatever that was. So the fourth power is the last thing that happens. It's the outermost function. So that's the derivative we take first. So I've got the derivative of some stuff to the fourth power. The derivative of some stuff to the fourth is 4 times your stuff to the third. So we're going to get 4 times our stuff to the third power times the derivative of the stuff. Okay, this is where things get a little extra weird. I need to do the derivative of the inside stuff. Well, here's the problem. The derivative of the inside also requires the chain rule. So to take the derivative of the stuff, well, I need to find the derivative of secant of some new stuff. I know green's not the best, but that's what I got. So, and this is, so secant and cosecant are especially kind of weird. The derivative secant of x is secant of x times tangent of x. And I really encourage everyone, when you're saying that in your head, to not just say secant tangent, but to actually say secant of x tangent of x. Yeah, sorry, I know. It says this is the new stuff. Let me just use black. I've got black. Why don't I use black? So, the derivative of secant of x is secant of x times tangent of x. The derivative of secant of some new stuff is secant of the new stuff times tangent of the new stuff times the derivative of the new stuff. So it's going to be secant of the new stuff times tangent of the new stuff times the derivative of the new stuff. So it's going to be secant of x cubed plus cotangent x times tangent of x cubed plus cotangent x times the derivative of x cubed plus cotangent of x, which is 3x squared minus cosecant squared x. So secant and cosecant are kind of weird in that when you do them with the chain rule, when you do the derivative of secant of some stuff, you get secant of the stuff times tangent of the stuff, right? So the stuff kind of shows up twice. But then you only get the derivative of the stuff once, because again, the chain rule, right, you're only multiplying by the derivative of the stuff inside stuff one time. So secant's a little weird that way. Definitely, right? The derivative. So I want to really emphasize here that you don't get secant tangent of x cubed plus cotangent x. Secant tangent is not a thing. Secant of x times tangent of x is a thing. Secant of x cubed plus cotangent x times tangent of x cubed plus cotangent x is a thing. The secant tangent, not a thing. You have to have secant of something times tangent of something.